the presentation and deeper questions at the end. Thank you.
Thanks everyone for coming. I'm Kangying, a fifth-year PhD student at Yale School of Management. The paper I'm gonna presenting today is called "The Virtue of Complexity Everywhere," and this is a joint work with my advisor Brian Kelly and Professor Samia Malama, who is sitting at the behind. Okay, let's start. So I want to start this talk with the principle of parsimony, which is brought up by John Tukey in 1961. So this is kind of like the textbook rule number 1 when I was learning statistics. From the textbook time series analysis of forecasting and control by Box and Jenkins, they say that it's important in practice that we employ the smallest possible number of parameters for adequate representations. So this is what we are doing when we are doing statistics and econometrics. But I'm bringing this up because the recent findings in the machine learning literature is really clashing with this idea. For example, recently the ChatGPT got very popular. Everyone is using that to reply email or anything else. And the ChatGPT is based on the large language model GPT-3. And GPT-3 uses 175 billion parameters. 175 billion parameters, that's a large number. And even in the finance application, Google can show in 2020 used more than 30,000 parameters for the return prediction by neural network. So that's also a large number of parameters. So those large models sounds crazy to Jenkins and Box and Jenkins econometricians. Not only that those models are super big, they seem to be profligate, but also those models are tending to be overfitting the data. So since they are overfitting the data, there's no error in the in-sample data. That means the out-of-sample generalization would be very bad. Is that true? This is not correct. And that is the whole point of today's talk. So we have seen that those large models, yes, they have astronomical parameterizations, and they also can exactly fit the in-sample overfit of the data that we are expecting them to perform that out of sample. Turns out to be the best models out of sample. So how could that be, and why could that be? We can clearly see that those modern machine learning literature has turned the principle of parsimony on its head. And this is also happening in the finance too. In the finance, we have seen a large literature about the empirical gain over the simple models. Recently, those literature are mainly focused on the empirical part, and there's a little understanding of why this happens. And this is also why there's a lot of pushback that people are saying, oh, your big model are overfitting the data, so you got good out-of-sample performance because of good luck. Is that real pure luck? So this paper, what we do is you're building the case for machine learning literature in finance. We're trying to provide a theoretical understanding of what is the behavior of the machine learning models in the high complexity regime. And our main theoretical result is that the portfolio performance, which is measured in the Sharpe ratio, is increasing with the model complexity. So that's our main result. And this is also why we call this paper the virtue of complexity. And in this talk, my main focus would be on explaining the intuition and along with answering the skeptics. I will show that the good performance out of sample of the machine learning models are not just pure luck. It's exactly what we should expect. So that's the main focus of today's talk. And after providing the theoretical result, I'm going to show the empirical support for the theory in the US equities, international equities, futures, and bond market. So the goal of the empirical part is to show the virtue of complexity can be enjoyed universally in all of these assets. And that's why we call this paper virtue of complexity everywhere. So that's the outline of today's talk. So let's start the problem formulation with a thought experiment. Suppose there's only one single asset in market, and the true DGP assumes that the expected return is a functional form of predictors G. And now there's an analyst trying to predict the returns. She might have access to some part of the G, but she doesn't have access to the functional form of F. It's just like the reality that we know there's stock prices, but we don't know how the stock returns are generated. This is a process. Since we don't know how the functional form F looks like, what we can do is that we make an assumption of model and try our best to estimate the functional form of F. So this is where the machine learning kicks in. So the analyst, what an analyst can do is that she can approximate functional form of F by the neural network. That is try to propagating the raw predictors GT into the neural network. So the interruptions can be picked up, the nonlinearities can be picked up, and at the end of the neural network, it's always a linear combination. So this is the process. In the first layer, in the input layer, that is just raw predictors GT. And then in the second layer, in the middle layer, we can propagate the G into the non-activation function F tilde. It's just like value or sigmoid. Then at the end of the neural network, we draw a linear combination of those signal S, and that is how we're gonna predict our returns. That's the how we're gonna process this problem. So that's our problem. We have the true model, which assumes there's a unknown functional form of F. And in the empirical part, we estimate the functional form of F by the neural network. But we have a question here, that how many dots in the middle layer we should use? So by the neural network, we know that as we are expanding the number of nodes in the middle layer, we'll get better approximation of the true functional form of F, because we'll have better specification of the true model. But on the other hand, as the model is getting bigger and bigger, we have to pay higher statistical costs because the estimation variance will be bigger if we're putting more and more parameters. So there's a trade-off here. Suppose we have key data points. The key question here is just to define, define what's the optimal number of features P we need to use in approximating model. Yes, please.
Just a quick clarifying question. So instead of going Y, you could also go P, but you choose to only have one layer and go Y. Why is that?
Because theoretically, this is how we're gonna process. If you choose like different layers, that can be also be like those number of parameters is extending. So it's the same as extending those parameters in one layer. So here we're discussing like how many parameters we want to add in this model.
But you could add them to the layers, you could make it wider or deeper, and you chose wider. And you choose wider because then it's better to prove stuff.
Yes.
Okay, great.
Yeah, we're using the canonical case. So this question can be pinned down by the two trade-offs. For the simple model, we get low variance, but there's that approximation of functional format of F. And for the complex model, we'll have better approximation to the functional format of F, but it's harder to approximate the model. So the central question is what P we should have. Or in other words, which effect is going to dominate as we extend the model. And the result is kind of surprising, that you should use the largest P the computer can compute. That means for whatever P we are using, we can add an incremental element so that we extend the model to be bigger and we can have better performance. So that's the result. And how can we get those results? I'm starting from the last, the OLS. Yes?
Sorry, could you just briefly tell us, because what is your objective function, or how do you, what do you mean with best in this sense? So
the objective function here is just to have better prediction.
But in which metric?
This is solving OLS. So MS.
So least square.
Yes. Okay, so let's start with the least square because that's the last layer of our neural network. when we're solving the regression, we're actually solving a system of equations. We have P number of observations, so we have P equations, and we have P parameters to solve. So that's the number of parameters we need to get the solution. When P is smaller than P, this is just the OLS, there's nothing surprise here. We can get a unique solution for beta hat. And what's interesting here is that when P is equal to T, we can still get a unique solution, but that solution can exactly fit in sample data. So that's the case for overfitting. We'll have that out of sample generalization here. But here, we don't need to limit ourselves to P smaller than T. We can push P far beyond T. And what will happen here is that we got more parameters to estimate than the equations we have. So in that case, the linear algebra tells us that we got infinite number of solutions. So how can we choose the unique solution? We want to choose the unique solution with the smallest variance. So we'll have the smallest forecast variance. And how can we do that? We're going to use the ridge list regression. So the ridge list regression is the ridge regression with this shrinkage going to 0. We want it going to 0 because we still want the solution that can exactly match the in-sample data. And the ridge list will make sure that we choose the solution with the smallest variance. So that's the foundation for how we're going to approximate estimate this model. Okay, so after we see foundation, we can see, now we can see the calibration of our theoretical model. First, we define the model complexity as the number of parameters over the number of observations. That's the model complexity. And here are two panels of the plot. The first panel is the auto-sample R-squared, and the second panel is the normal theta. The x-axis is the model complexity. As complexity is equal to 0, we can see the R-squared is close to 0, because right now, the model is just a coercive approximate of f, so it's a misspecified model. That's why we got the R-squared very close to 0. And when c is approaching 1, we're approaching the case of overfitting. So the R-squared are dropping the ridge list R-squared. This is the ridge list, and it's dropping to negative infinity because the other sample generalization at the overfitting point will be very bad. So this is what we already know. It's just regular OLS. It's nothing surprising here. But for this plot, the interesting thing here is that what will happen when we push the c larger than 1? Is the R-squared gonna drop again, or is it gonna bounce back? The intuition tells us that the R-squared probably drops again because we're estimating an even bigger model. Is that true? So our theory part tells us that this is not true. Counterintuitively, when c is larger than 1, the R-squared will be better. This is very surprising. So why does it happen?
Sorry.
Yeah.
Sorry for cutting. So what's your definition of R-squared? It's not some square correlation coefficient, I assume.
This is just the R-squared for to check what proportion of the error in the auto sample can be predicted.
Yeah, but why is it negative?
Because this is how can be. The negative just means it predicts the worse than the constant 0. If the prediction is predicting the time series worse than constant 0, it will be negative.
Okay, so
Yeah.
thank you.
Okay, so why does this happen? Remember that when c is larger than 1, we got infinite number of solutions. So then we use the ridge list regression to choose the unique solution that can exactly match the in-sample data. And as we got higher c, that means we are putting more and more s into the middle layer. And as a result, we can have more solutions to search over for the unique solution with the smallest beta norm. This is why when c increases, the norm of beta is decreasing. And as the norm of beta is decreasing, that means the forecast error is also decreasing. And this is why the R-squared is bouncing back. So that's the intuition for why we can have better prediction in the higher complexity region. So this is related to the topic benign overfit and double descent, which has already appeared in the statistics, which challenges the dogma of parsimony. And now, after we see the better prediction, we're curious how it can be applied for the trading strategy. So here's the plot for the trading strategy. Our trading, yes?
Sorry, I missed. Why is this like double descent and missed the point? You mentioned double descent, you mean in learning sense, right?
Yes.
Sorry,
So the double descent. So double descent shows the double descent shape in the MSE, right? And R squared is another like bias variance form of MSE. You can see that R squared is like a projection of MSE. Yeah. So they're the same. I'm just showing it in different variables.
But it's not a lot of effort, it's a lot of complexity. Double descent is a lot of effort.
It's also complexity. It's the number of parameters in the, yes. It's about number of parameters, not about that. Okay, so for the timing strategy here, we are using a simple timing strategy here. The timing strategy we're using here is just assume the portfolio weight is equal to the expected returns. So that means if we're expecting higher positive returns, we just long this portfolio. And if we're expecting a negative returns, we just short this amount of positions. So this is optimal for the Sharpe ratio maximization. And for the strategy variance, it has the same pattern of the beta norm, because the volatility and the norm of beta are both a reflection of how the forecast variance are. So the intuition for those patterns is the same as the norm of beta. And for expected returns, it has the monotonically increasing pattern. And this is interesting because, so why this happens is that when we have more complex model, we have better approximation to the true functional formula F. And this is why expected returns are increasing, because we have less misspecified model. Now, combining the expected return and volatility into the Sharpe ratio, we can have the increasing pattern of the Sharpe ratio. So the Sharpe ratio here is increasing. When C is smaller than 1, in this part, the Sharpe ratio increases because the expected return is increasing. When C is larger than 1, it's still increasing, both because the expected return is increasing and the volatility is decreasing. And when C equal to 1, the richness case of this point is dropping back to 0. It's not because the strategy is not profitable, because the expected return is still high, but because the volatility is going to infinity. That's why the Sharpe ratio is dropping back to 0. So from this plot, we got our main theoretical result that the complexity is over true. So come back to the question the analysts asked, that what P we should choose. There are two effects for the trade-off. Now the trade-off is explicitly stated here, that the approximation benefit will dominate the cost of heavy parameterization. So that's the main result of the theoretical part. So those are just the calibration of our theory part. I'm not going to go through those complicated theory part. Yeah, and behind those plots, there are general and rigorous theoretical statement and proofs. Okay, now let's come to the empirical part. For the empirical part, we're curious like how the virtual complexity works. And what we can do is that we can analyze the exact empirical setting that's analog to the theoretical part. And we check the empirical part with the US equities, international equities, futures, and bonds. So those are the data that I'm going to go through fast. For the US equities, we're using the Fama-French 5 factors, the momentum, and 153 US equities from the Jensen, Kelly, and Peterson in 2021. The predictor we are using are Welch and Goyle 15 predictors, and also factor momentum based on Gopan and Kelly in 2019. The forecast target for international equities include the excess market return of 93 countries, from Jensen, Kelly, and Peterson, and the information set are momentums. For futures, we use the 44 futures from the SCF database, and the information set include the momentum and carry momentum. And for bonds, we are using the setting from the Cochrane Piazzi to forecast annual returns, and we use the information set of log forward rates. Okay, so we have seen those data, and we found the predictors we're using are just small number. They're less than even like 16. So recall that the empirical model we assume the expected return is a linear combination of P predictors, P signals S, and we want to see this linear model in the high complexity region. So how can we do this in the high complexity region with only like 16 predictors? Here we are going to use the methodology to transit from low to high complexity with the same underlying information. This methodology is called the random Fourier features. So the random Fourier features contains the two steps. The first step, we draw a linear combination of the raw predictors. And second step, we feed those linear combination into the nonlinear activation function f. Here, the random Fourier features use the nonlinear activation function sine and cosine. But if you're doing like testing, it's also robust to other activation function like value or sigmoid. So by this framework, the good thing is that we can control the number of signals we have on our hand. If you want just like very simple models, we can just draw one linear combination. If you want very complex models, we can draw like 10,000 combinations. And this is how we're gonna study the model in the high complexity region. For the gamma, we choose the mixed gamma from 0.1 to 16. This is just a parameter to decrease the effect of the scale for different predictors. And this process can be seen as the two-layer neural network. So in the first layer, the input layer, this is just the predictors. And in the middle layer, we propagate the G into the linear combination, then put them into the sine and cosine function. So in this process, we can have the nonlinear transformation of the raw predictors G. And we can get as many nodes in the middle as we want. And at the end of the layer, that is the linear layer that we use to estimate the beta with regression. So that's the process, how we're gonna proceed with our empirical analysis. In the empirical analysis, we use the 12-month training window, which is short. So we can have this model into high complexity with relatively small number of P. It's just easier to compute. And also we want to show that if the virtual complexity can be enjoyed by the very small number of training window, the longer window will also work. The model complexity is from 1 to 12,000. So the highest complexity is at 1,000. And the shrinkage, log of shrinkage is from -3 to 3. And here's the detail of the empirical procedure. I'm not going to go through it because of the time. Okay, let's jump into the result. There are two rows. The first row is the expected return. The second row is the volatility. The panel A is US equities with Boyle-Welch signals. The second panel is with the momentum signals for US equities. The panel C is the international equities with the momentum. So we can see the expected return is monotonically increasing, which follows the theory part. And the volatility is going up first before C equals to 1, then going back down. Somehow. Sorry, this is.
You could try clicking on it on the computer. Click on the screen.
No, just touch.
No, doesn't work. Okay, sorry. Okay, so here are the plots for futures and bonds. They all of them has this similar patterns. So broadly speaking, the outer sample behavior can closely match with the theoretical patterns. The variance exploding as equals to 1 then recovers in higher complexity regime, and the expected return is increasing. So combining them into the Sharpe ratio, you can see the Sharpe ratio is also having the increasing pattern. And this is where we draw the conclusion of this paper, that the virtue of complexity can be enjoyed universally for other asset classes. Okay, so here's the conclusion, that this paper is based on the background that the machine learning at broadly applied into the asset pricing and the asset management. And in this paper, we provide the theoretical analysis about how the model behavior and portfolio behavior looks like in higher complexity regime. And the main finding is that the higher complexity would improve the model performance. And for the virtue of complexity, the main takeaway is that we don't need to limit ourselves to the low complexity region. We can push the number of parameters far beyond the number of observations, and we can find the model performance improve when we are pushing it in the high complexity region. So just know that this paper is not a license to add arbitrary predictors. We cannot expect that we add some white noise predictors and found the model performance gonna improve. So what we recommend here is that when we are making predictions, we include all the relevant predictors that have some predictability, then further extend the model with nonlinearities. So in the empirical part, the main finding is that the virtue of complexity is universal. Those Sharpe ratio is increasing with or those 4 kind of assets. And the high complexity mainly comes from the nonlinear prediction effect. Okay, we've got some time. So let's come back to the principle of parsimony. This paper is clashing with the philosophy of parsimony. So let's end with 2 quotes from the George box. The first quote is that all models are wrong, but some are useful. And the second is that since all the models are wrong, the scientists cannot obtain the correct one by excessive elaboration. On the contrary, following the William of outcome, he should stick an economical description of natural phenomena. Just as the ability to devise the simple but advocate models is the signature of the great scientist elaboration and over parameterization is often the mark of mediocrity. So is this true? Based on this model, we can actually change the outcomes razor to outcomes blunder. That yes, the principle of parsimony holds only when we can correctly specify the model. So since the small model is only preferred when it's correctly specified, and in reality, we can never correctly specify model. What's the logic conclusion? That don't use simple model, just use the large model that your computer can compute. That's the main takeaway. Thank you very much.
11 minutes, so we can have a discussion for 11 minutes.
11 minutes. Oh, that's great.
I have one comment, which is this works only if you have a very large amount of data. There are many problems in which we don't have much data. So it's not relevant for those problems. Box advice is very good for the cases where you have only a fairly limited amount of data. If you could give some measure of, how much data you need for your, and I know this is nebulous, but that's why your paper is nebulous. If you could give some sense of how much data do you need for your kinds of results relative to the number of parameters. It's really about data relative to parameters. And those are both hard things to have a metric for. But if you have a large amount of data, enormous amount of data relative to the number of parameters, If you have a billion parameters, but you have, a quintillion amount of data that you're estimating with parameters. A billion is not a lot of parameters for a data set. There's a quintillion data points, right? That's the metric that you need to use.
Well, so for this paper is discussing that when we have fixed amount of data,
Yeah,
how many
I'm sorry, that's
parameters?
not the interesting question. The interesting question is how much data versus how much parameters.
Yes, but for the empirical part, we already know what data we have. Yeah, if we can get more data, of course, the more data is better. But
we need a practical guide. When is it good to use, when is the box right and when are you guys right? And saying, well, we're just assuming a fixed amount of data doesn't really help.
well, so you're saying that we have a large number of data, but we choose to use a small number, or we can choose to use a large number. So what's the?
I think my point has been made, and I will let other people ask questions.
Okay, thank you. We can discuss later. Yes.
Question, sort of free to tell me, but I have no idea what I'm talking about. So, I guess sort of in my traditional head, I would view model complexity being related to the covariance between the data and the fitted values, right? High level covariance would be a very complex model. But when you get to this regime where the number of parameters exceeds the number of data points, you sort of already maxed out my measure, now you're able to select among models that are equivalent to this definition. You can choose one with lower and lower on the coefficient. So it's almost like you hit this transition point, and now you can you have a bunch of models that are equivalent in my old-fashioned definition of complexity, but really I can select one that's simpler, that's more parsimonious. So this is indexing the complexity of the model by the number of parameters might be a little misleading in a way, because once you hit this point, you're actually choosing simpler models. You're privileging simpler models among ones with equivalent predictive power, if I understand what's
Well,
going on correctly.
I think
I may not.
it depends on the definition of the model complexity.
Yeah, exactly.
So the model complexity is defined for like before you got your result. Yes, after you got your result, you found the beta, like the beta only have non-zero parameters for like 10 out of 1,000 predictors. But that doesn't mean this model, when before you're estimating, is simple. It just ex post, it's simple. And the model complexity is focused on the ex ante data point and the model estimation. Is that clear?
I have to think about it. So,
Okay, we can discuss more. Yes.
So I'm just a little bit curious as a model complexity. So I think you're kind of defining complexity by like number of parameters in the model. And you also seem to be kind of viewing this from the perspective of a neural net. Are there any differences in the results when you look at like just for instance in the context of a neural net? Whether you're making a wide net or a deep net, like a more parameters is really better than one type of like a deep net or a wide net or something like that.
For this paper, no, we're just using the simplest OLS regression form. But I know there are papers discussing whether there's finite overfitting or double descent in the neural net. So if you check, I know there's some paper about it. They can also find the double descent with the neural net. But I'm not sure they discussed whether it's wider or deeper, that makes sense. Yeah.
I'm just curious.
Yeah, I'm not sure about the symmetric between getting deeper or wider. Yeah.
Different types of complexity.
Yes, please.
Yes, so I was curious about like this ratio of complexity, if it's also virtuous, if I kind of want to forecast out of the sample range. So I mean, to be fair, I don't know much about predicting asset returns, but thinking of assume I don't know how to forecast some stock returns maybe, and then know okay, there have maybe certain employment growth, certain revenue growth, I don't know, and then there's I think I'm not using this, but then there's movement happening and like I observe values I've never seen before in my sample. And here with okay, this complexity still reduced in such situation, or is also the model extrapolate? Is it like
So,
there was a lot of curiosity.
so you're curious about how that works for like single stop.
It would work, it's like,
I'm not sure I understand the question correct. That are you asking like how does it work for individual stop? Or how do you like?
No, I mean, I guess like okay, you fit your model and you have like you use the data and I don't know, assume there's economies in normal times, the data always like a certain range of, I guess, for example, film level employment growth will always be, I don't know, like 3%, but then I don't know, something odd happens, I don't know, there's like somehow like a regime change, like say, I don't know, there's like a pandemic and then you observe much higher levels of film level employment growth, for example, so out of the range of the data on which you trained model, I was curious whether in such cases there would still be the complexity would still be reduced in such cases.
I see. So I think this can be separate answered like in two ways. The first, that what kind of predictor we want to choose. I think this framework is flexible about what exactly predictors we need to choose. We're just discussing the pattern here. If you put the useful predictors inside the model, then you can get the same pattern. What it changed is just the scale of the Sharpe ratio or the R squared. And for whether this model can capture the structural breaks, I think I'm having another project doing it. The answer, like the initial answer is yes, but there's no conclusion from this paper.
Two more questions, depending on how concise they are.
I think you introduce a very important distinction at the end of your presentation between the complexity induced by the number of parameters in the given layers and the complexity issued from the number of explanatory factors, what you call predictor. And I would be tempted to say that Occam refer more to the number of explanatory factors than the number of parameters you need to get the right non-linear shape.
Well, that's a good point. Right now, we are having the S. It's actually because of two reasons. Because we want to get some non-linearities of the raw predictors, and what's most importantly is that we just got limited number of raw predictors. So we're not able to proceed or study this model in a high complexity with just like 4 predictors, and that's why we're using a large number. So if you got like 10 millions of raw predictors G, actually we'll get the same solution. So I just want to clarify here, the S is just to, it's a tool to study the model in a high complexity region. Yeah. Yes, please.
So I'm trying to get like an intuition for the change in the inductive bias of the neural network as you increase the number of parameters, and based on some other stuff I just sort of sanity check. Is it approaching a Gaussian process as you increase the number of parameters? Is that like something overall, or am I misunderstanding this?
So this paper is using the random Fourier theory. So in this paper, the theory part, we assume both the number of observations t and the number of parameters p going to infinity. Because the number of p is also going to infinity, that means the regular the regular asymptotic piece doesn't work. So that's like what you asked, that the regular asymptotic and the derivations is not working. All of those derivations are based on random matrix theory. Yeah. Like law of large numbers doesn't work here.
Okay, thank you very much.